Good afternoon. Okay, so the slide is visible. Hello, slide is visible.
Yes, sir.
Yeah. Oh, thank you. Okay, so we are discussing the linear support vector machine, and whatever we have in last class, what we have formulated that as a problem, that this support vector machine is being formulated as the problem of this support vector machine formulated as a constant optimization problem, such as we have to find this W and B, and W is a vector where this xi of W is basically half of W transpose W, or you can say this is W norm. That should be minimized. To be minimized. And for this are the data points. Xi is a time, some dimensionality is there. This is the class information. And such that this is our subject of constraint. This WTXI plus B greater than is equal to 1. So that is whatever I just rewrite this thing. Okay, so that is our idea. And for this particular thing, what we have actually formulated, that we have a Lagrangian dual formulation, and we formulate this particular problem in this form for alpha 1, alpha 2, alpha n. These are the Lagrange polynomial. So Q alpha is equal to summation of alpha I minus half of double summation alpha I, alpha j, yi, yj, and these two vector xi transpose xj should be maximized. The same thing. This actually constant with constant problem. This is unconstant problem, and there is a another thing. This summation alpha I yi is equal to 0 for alpha I greater than is equal to 0 for alpha I. So these are the two assumption. And another very important assumption that we make, that is most important, to if you can say this is a kind of your feature space, these points, what these are linearly separable. Okay, that is most important assumption for this. This linear separability issue is a most important, you can say, from the SVM viewpoint, because in general SVM is going to find out some sort of decision boundary, maybe straight line, maybe plane, maybe hyperplane, in anything that is linear in nature. So that training examples are linearly separable. This linear separability is one of the major issue in kind of support vector machine. Now, the question is that if these data points, what has been given, if this data is not linearly separable, then what we will do? Or you can say these data points are a bit noisy. Maybe there is some sort of outliers in the data. Okay. So these two are kind of expose the similar problem, but not the actual similar things. But anyway, that we have to deal with, that how actually we try to deal with linearly non-separable data. That is the main question. So extend the definition of maximum margin to allow the non-separating planes. So that is we are trying to understand here. Actually, what I'm trying to do is basically this. Here, what we are going to do, just let try to draw this. This is your, let's say, a decision boundary, and now you see there is a another. This is the margin, and this is another margin. So this is the ideal case, or okay. Now there is a some sort of data points are these. Now, is it possible that some data point are here, or some data pointer here? Okay. So these data points are, you can say these, this is the blue data points, and you can take another thing, just if we, that we can gray some this. So this is should be a kind, and there is a data point something like here, or here. Okay. Now you see that these data points are kind of noisy to our settings. Now you see that these data points is supposed to be uh, this side of this guideline, but there is a some sort of drift. If you can perpendicular to that, this is the kind of error. Okay, and this is another error. This is the perpendicular of this. This is another noisy point. And here, this is again this kind of data. This is the kind of noise for this. Okay, so this is the another noisy point. This is another noisy point. So we put it 9. So this is the point. So these are the some noisy point. Okay. The question is that how, if this is the situation, how we deal with this kind of data. Okay. So, but before we going to that, the solution of the problem. Okay, this we are already. These are the previous things. Okay. So that this is the idea, that this is the kind of noisy data what I'm going to just show. So before to handle it, there is a few definition, that is some sort of hard margin classifier. So far we require all data points to be classified correctly. There is true net, no training error. That we have so far, that is called, whatever we have discussed so far is called hard margin. Whatever margin we have said is called. What if the training set is noisy? So use very powerful kernels one. And another solution is that this, what that actually I'm trying to. So that you see that in this case, these are the points, that these points are noisy points. Okay. These points are noisy points. Okay. So these points again, there should be some something that this, so this is, there is some point, so it is a noisy. So what we're going to say that we propose a different kind of thing that is called soft margin classifier. Now here soft margin classifier means we somewhat relax, give some relaxation of this noisy data point through, we called the variable called slack variables. So what we are going to do, we define these slack variables here. That is going to allow to slack variables is a slackation kind of from the point of, through slack variables we allow some noise or some noisy data, okay, to our classifier. So slack variables can be added to allow misclassification of difficult or noisy example. Okay, so the idea is this: we allow some sort of noisy, not what should our quadratic optimization criterion be. Now you see that our quadratic optimization criterion, previously what was the criterion? That to minimize half of W into W transpose. Now we put, there is a some sort of C is a some constant that is to this training error. So we are allowing some noise or error at the time of training through slack variables. And this is actually these slack variables that sees what this error, actually this error we are calculating. This is error, this is error, this is error. So this error we are calculating using this slack variable. And what are the these values? What are the genuine value? These are slack variables are 0. These are the genuine values. This for this particular point, which are not misclassified, or this is the not the proper side of this our this flat margin classifier, that this slack variables is 0. Otherwise, there is some non-zero slack variables. So we put this error. Now, what is our thing? This instance is the minimization function. We want to minimize this number of slack variables. So that is our thing. How you put our because this function is basically what this function is basically giving you the where you put your these guidelines, or you put your decision boundary along with guidelines. The problem is that it is no longer a quadratic optimization problem, and we can't use this quadratic programming solver to solve it because because of this thing. Okay, so what we have actually did here, that we put some sort of error, or you can make you can say also that this is a kind of a some sort of relaxation, you can say. Okay, that from that is a slack variable, relaxation, something. Okay, so now that soft margin classification, then what? As you see, these are the slack variables, and what we have to, this M to be minimized. With M, this W minimize W transpose W W transpose W uh, or W dot W transpose plus C of this summation. Now you see this. What is the C here? Because I said one concept of C. C is, I said, C is a constant. That constant is going to give that controls the relative importance of maximizing the margins and the fitting the training data. So there is a two issue now. This is what this particular thing is basically what this is trying to maximize the margin. Okay, this particular expression, and this expression is basically what it is doing. It is basically doing the fitting the noisy data. So some succession. So this C is basically a control variable that put how much slackation we can give. So this kind of prioritization. Let's say this C is very point 0.1. So the slackation is very less or something like that. Okay. So controls. So this way we can control overfitting also, because definitely that is the thing. Because this, if you give this C actually going to, if it is a very carefully chosen, then it can control overfitting, because somewhat giving this slackation, it kind of, so slackation means what? Now you can understand slackation means what, that if there is a, let's say this kind of our previous example and this, so the thing is that this is the some sort of generalized curve, but are we the thing that this slackation means what? Slackation means that it is something like that. Okay, so this relaxation is being given. Now this thing will reduce or you make more, it make more, there is a tendency, it increase the tendency of overfitting. Okay, so that C is control that overfitting. That is one thing. Now the question is that from the point of view mathematical representation, now this like variables is that W, if W of xk plus b greater than is equal to 1 minus this slack variable if y is equal to 1. So it's a positive example. And wxk plus b less than is equal to minus 1 plus k plus xi k if y is equal to. So that same thing equation, it to this two equation, it basically if you adjoin this, if you just joining these two equation, we can say yk into w of xk, w dot xk plus b greater than equal to 1 minus xk, for k is equal to 1, k is equal to, and this xk greater than, so xk is greater than not 0 because of this atom. So one important thing is there, that this soft margin classifier not only depends on your support vectors, but depend on this noisy data point. Okay. So initially it was dependent mainly on the support vectors and the decision boundary I'm saying, but here it is depends on not only support vector but also the slack variables or noisy uh, the, these noisy data points which have been given slackation or relaxation. Now the same thing we are going to do, that we put this the same thing we have to put is the Lagrangian multiplier. Now you put here this is our Lagrangian primal problem is this half W transpose W, you can say, you can put a transpose here, or this is C of, now it is a new term we put. Now it basically the same routine we will do. It's not a very big issue because we already understand how actually this Lagrangian multiplier is going to work. Now you put, if this is the primal problem, so we put primal problem, and then we put this alpha beta, this Lagrangian multipliers, you can say that this alpha I, the yi, so this is the primal problem. So alpha I into, so these values yi w x into w plus b minus 1 plus xi I. So that this xi I we put because of this. Okay. And since there is another value, that is alpha is, there is another value of this, and this particular value xi k is equal to this. So we put these values of this coming bi of xi. Okay. So this is the, you can say the formulation. So we make this constant optimization problem to unconstant optimization problem using like that. Okay. Now same thing we're going to do, that we put the dual formation. The dual formation is something like that. Find alpha 1, alpha 2, alpha n, so that these are the Lagrangian multiplication multipliers, so that this max this G alpha, that we're going to, that we can say the minimum of these is basically the maximum of this. That is the dual problem. So maximum of alpha J alpha is basically Now we can write this. I can write it that I is equal to 1. This is total number of data points alpha I minus half of 1 to m alpha I, alpha j, yi, yj, and that is most important, x transpose I, x transpose x of j. So this is actually, these two are vectors. These are actually the dot product between xi and xj. Okay. So in case of our linear SVM, that this was the same, but what is the difference here? So the main difference here is that for linear SVM, this I is equal to m, alpha I is equal to 0, only this. But here you can say this alpha I greater than is equal to 0. But here, this alpha I greater than is equal to 0 is okay, but it is less than is equal to c. C is this control variable that controls the overfitting, or you can control the fluctuation. So this is the basic idea, where I is equal to 1 to m, alpha I, y is equal to 0. So these are the noise accounted version accounted that we are accounted with this slack variables. Okay, so that is basically been done in this formulation. Now, if we get what is basically a now xi with non-zero vectors, definitely this xi, that is the data points actually, with non-zero non-zero alpha is, that we said that this is our support vector, as you said before. Actually, that means non-zero alpha is basically uh, contributing. Other, those with alpha with non-zero zero values, that is not contributing. And essentially, this is true because the other data points are not important for this decision boundary case, or basically the margin, the what will be the width of the margin. They are not going to decide. They are not taking part to decide it. So solution of the dual problem is definitely this. This is the most important problem, that alpha I, yi, xi. Okay, and that is a class, there should be a class B, something like that. So this B is equal to yk 1 minus alpha this yk minus this 1 to m summation alpha yi xi yk. So this is the B. And now most importantly, this is the testing thing, that for any k such that alpha k is greater than 0, because alpha k means this is the support vector. For classification in this test case, when there is a new point xi is coming, so we can calculate alpha I, yi xi with this xj means is a new value. This is the new value, and plus b is this defined with this, and we have to find out that it is plus, so it is a plus one, it is minus, basically it is an other side. No need to compute the w explicitly. We even don't need to calculate the value of the w. We can get this in this way. We can actually find out the classification of a new novel point, no new point, the testing points. So this is the basic is called submargin classification. Okay, so we summarize here that this is the old problem, that is the hard margin classifier. Okay, hard margin classifier. So this is the formulation. And for your new, this incorporating service is a soft margin classifier. This is soft classifier. So this is find WXP so that C of summation of xi I is minimized, and for all these points with object to the constant, these values in 1 minus xi. Parameter C can be viewed as a way to control the work. This is the summary. Okay. So classifier is separating. So this is the summary of linear SVM. The classifier is separating hyperplane because it depends on the dimensionality of the data. Most important training points are support vectors. They define the hyperplane. That is also we understand. But quadratic optimization algorithm can identify which training points xi as support vectors with non-zero Lagrangian multiplier alpha. That is the solution of this problem. Both the dual formulation of the problem and its solution training post appear inside the dot product. So these are actually that thing will be here. This is the important. This is the dot product. So this is should be maximized. And here also this is in bit misplaced. So this should be most important. So this is the overall of linear. So if you have any question, you can ask. Otherwise, we'll go to the next part. Now, with this soft margin classification is somewhat works fine for the noisy data. The noise is not that much. But if the noise is very high, or that is that something like this kind of problem. So this is a kind of circle. Then this kind of thing not going to work. Okay. To some noisy example, it can handle. Some small outliers they can handle. But if this is the data distribution itself is so much complicated, there is no linear separability at all, then this kind of problem, this kind of classifier is not going. So that is a data set that are linearly separable with some noise. That is what great. But if we're going to do it, if the data is just too hard, that means this kind of data. Now, the idea is basically this. How about mapping data? So what we're trying to do that let this is your dimensionality. Okay. So and this data are something. They are very badly clustered. Okay. So definitely there is no linear separator. But then is that this is let x1, x2. Now this is the two-dimensional case. Can we project this data to a higher dimensional space? Okay, now you see this example that there is a red dot and there is a blue dot and again red dot. So definitely there is no linear separability. But if you project this data to this is x dimension, so one dimensional. Now if we project this is the two-dimensional data, that is one is x and one is x square. That's what exactly they do. Now you see what we actually going to happen. Now let's say this is 1, this is 1.5, this is 2. Okay, and this is what, let's say is a 4, the 5 and 6, or 8, or this is what, this is also something like that. They actually make it a bit wrong, but anyway. Hmm. Yeah, let's say it is 1, 1.5, minus 1, minus 1.5, minus 4, minus 6, something like that. Now, what happens if you square it up? Then this kind of thing will happen. This will 1, 15, 2.25, then that is 4. Okay, but it jumps to the, this, it is going to the 16, 25, 64, and something like that. So it is there, and definitely 1. So you can generally get this kind of it. So now it becomes this. If it is x and x square, so definitely these data points are coming what? This is something like 1, 2.5, 4, this way, but it will come. So it will come like that, 16. So here, so here, 64. Here also you can get these, these. These are the 1, 1.5, then 16, then 36, something like that. So you can easily get a find a kind of linear separator like this. This is a linear separator. So what is not possible in a particular dimension, it may be possible, but we don't know the which dimension. This is just by luck we get this idea. So that is possible in higher dimension. We can find a kind of linear separator, maybe plane, maybe hyperplane, maybe anything. Okay, so that is the basic idea. So what we're going to do, we do a nonlinear transformation of the data points from the lower dimension to the higher dimension. Here exactly, the original input space can always be mapped to or project to some higher dimension of feature space where the training set is linearly separable. Here you can see that example we have so that if there is a circle kind of this required for this, so it's never been nonlinear. It never been linear. So what we see with this phi x, this x to phi x. So phi, this phi is a nonlinear transformation. Okay, we put a nonlinear transformation here. Okay, so if you do the nonlinear transformation, that we don't know which dimension, but we put a certain dimension. You can see between this blue point and this red point, there is a kind of plane exist, and so this is a separating plane because this red point in another side of this plane, it is not that much visible because of this the limitation of our drawing, because we cannot go beyond 2D in this kind of space, but it's a 3D space. And so this is actually this is the place. In upper one side is blue, another side is red. So this is the space actually. Okay, so this is the way we can separate it out. So this is the idea is we put a nonlinear transformation over data points. Okay, now this is very important. But it is whatever we are thinking is not always be very easy, because you see that this when we are doing this classification, major thing is here, because this is sorry, change this color. So the major thing is here. So this xi transpose xg, because this is the this dot product. So now if we do this, this is the d square, d is a or d of lesser dimension. But if we do that this xi xj, and if we transform this xi to phi of xi and xj to phi of xj, okay, now this is xi, actually this should be xi of this. So then it is this dimensionality that was d previously, now this d. And if d is greater than d, then the problem is that this thing will be, this is very increasing the d, the computational cost will increase substantially. So it is computationally infeasible. This kind of mechanism is computationally infeasible. Okay, that is the one of the major challenge of this sort of solution. That dimensionality, increase of dimensionality is a solution, but it increases the uh, computational cost exponentially. Okay, understand? Mainly if this d is very greater than equal to, a lot is much greater than small d. Okay, so the same problem, that this kind of thing problem. So there is some sort of understanding here, that already we discussed, that this kind of thing is possible with uh, projecting this space from some d-dimensional to some higher dimensional, where d is equal to d, some mostly this is d. Now what to do? Now what we are going to do, yes, now we use some sort of function. It is called kernel function. What is kernel function? Kernel function is a kind of function that the linear classifier relies the dot product between vectors this. So kernel function is such that, let's say k is a kernel function of xi xj is basically xit xj. Okay. If you can write in this way, that means if every data point is mapped into higher dimensional space via some transformation, the dot product becomes, so k of xi xj, it now this due to this function, I should write x, what happened, xi become xi of xi, xj become xi of xj, and this is the transform. That is fine, this is not an issue. Issue is that this k of x of xj, so this is the this function k of xi xj can be represented in this way. So it is can be, since it is now xi becomes xi of xi, so that is xi of xi dot product, or this is of xj, xi of xj. Okay, so kernel function is such a function, so that it's in higher dimension, it can be computed with the individual size, multiplication individual size. So a kernel function is some function that corresponds to an inner product to some expanded feature space. You can understand? Now our xi dot xj, now it becomes xi of xi dot xi of xj in the higher dimensional space. Get it the point? Using this. So those function is basically going to give you this flexibility. We call it kernel function. Okay. So take example, you can understand it very easily. The two-dimensional vector, let this x1, this, let's say this is a two-dimensional vector, x is basically x1, x2. This one is a vector. And now this, how this k is defined? This is defined k of xi xj is defined by, this is the function f of, this is f. So 1 plus xit dot xj square. Okay. This is the function. Kernel function is the function. So in the higher space, this will be. So now you need to show that this thing, k of this, is basically what? Xi of xi transpose xi of xj. Okay, that will have to show. This thing is basically this. Now if you do this particular thing, 1 plus xi transpose xj square, we can get these values. 1 plus xi square xj square plus 2 of xi xj x2 xj and x. These are the normal mathematics. And after that, this particular thing can be written in this this vector product. That 1 xi squared root 2 xi1 xi2 xi square root 2 xi1 root 2 xi2 transpose. This is one vector. Another is 1 xji square root 2 xiji into xj2 square root 2 xji. So these two vectors. And that two vector is essentially what? This vector is basically your xi of x1. And this vector is basically your xi of x2. Okay, so this, so we can get this. Okay, so this is basically this xi of x is basically, this is a higher dimensional data representation. Okay, so this is the way we can show that this kernel trick is going to handle the exponential. There should be no exponential data this computation. So it's very, the computation become more or less um, much bounded. So this some function case is checking that this is can be cumbersome. So there is a Mercer's theorem. So this is just, you understand. Proof of this theorem is not in our scope, but every semi-positive definite symmetric function is a kernel function. Is a kernel. Okay. Semi-positive definite symmetric function correspond to a semi-positive definite symmetric Gram matrix. So this basically, so this is just our result we should. This is important. What are the different kernel function exist? Okay, so it's a linear kernel. This is the linear. This is the same thing. Nothing else. So this is almost. This is just LSVM. Okay. Now this is a polynomial kernel. We saw it one example where 1 by 1 xi xj xi transpose xj. This is example we have shown where p is equal to 2. That example. So it's a polynomial power p. So it's a polynomial kernel. Next is a very, very well-known function. It's called radial basis function. But the type is a Gaussian in nature. So k of xi x is exponential xi minus x square by 2 sigma square. So you can say that if time permit, we'll see that what is RDF. So this is very interesting. So that, and another term, this is the sigmoidal combination, tonnage B0xi transpose x plus bi. So this is also. So these are the different uh, versions or different kernel function. Now you can say these kernel functions, you can also design your own kernel function. Only thing that this particular thing we have to maintain this, that particular function, we say that is k of xi xj is k of xi xj is basically xi of xi xi of xj. So this, that is the thing that you have to maintain. Okay. Now for a different application, for different NLP application, there is some sort of kernel function. There is for some big data analytics, computer vision. So there is a lot of different kernel function as well. And there's a lot of research is also going on. Still, that people are asked and just coming with different kernel functions. So that it, so kernel function can be thought of a similarity measure between the input objects. Okay, so input objects is basically this. That is actually, this is a mapping from xi is a mapping between xi to xi of xi. So that is that mapping. Not all similarity measures as a kernel function, definitely that is the thing. Because that we have to, so that for those xi xi of xi, see, that is the basic thing. Mercer's condition state that any positive similarity kernel is a kernel. So this is the, can be expressed as a dot product in the higher dimension. That is also very important because this is that handle the computational link, that when the computationally feasible, that make this kernel, because the dot product in high dimensional space, dot product is not that complicated. Okay. Now you can say this is a linear polynomial, the second order polynomial. This is the fourth order polynomial, and these are eighth order polynomial. So these are some examples. You can see the Gaussian kernel is that these are the data points in this way, and how the Gaussian kernel is basically used for this kind of thing. So these are the Gaussian kernels. So, nonlinear SVM, mathematically you can say dual problem formulation, we can say this maximized, and now it is, we put a k here, and this is the same. The solution is basically we put a k of this. Optimization technique for finding alpha is remain the same. Okay, so this is the idea. So in summary, SVM locates the separating hyperplane in the feature space and classify point in that space. Does not need to represent the space explicitly, simply by defining the kernel function. The kernel function plays the role of the dot product in the feature space. But what does this mean? This that it does not need to really represent the spaces. That means W we are not going to discuss. Without W, just using the dot product, we can get. So flexibility in choosing a similarity function, sparseness of the solution when dealing with a large data, set of data, ability to handle larger feature space. So you can see all this we have discussed. Overfitting can be countered by soft margin approach. Nice math property, so it's mathematically nicely explained, and its feature selection is very. So what is the application of SVM? It is very much useful in text categorization or hypertext categorization, image classification, bioinformatics, protein classification or cancer classification, handwritten correction recognition, and next. So What is the weaknesses? That is sensitive to noise. Relatively small number of mislabeled examples can dramatically decrease the performance. It only considers two cases: how to do multi-class classification in SVM. So with this we can rarity of an SVM output one SVM output is two. Learns output X. To predict the output a new input just with each SVM and find out which outputs the prediction farthest into the positive. And that is the solution. So this concludes the support vector mission. Next week we start another supervised setting. Thank you.